December 19, 1944. Spanning 3 combat zones across 6 million square miles, American machine gunners submitted 47,000 after-action reports. The data within these documents would demolish 6 decades of military engineering wisdom. Gas-operated machine guns, the recognized standard, the validated technology, the design every authority insisted was superior, logged a 34% malfunction rate in battlefield conditions. Browning's recoil-operated weapons, just 3.2% identical ammunition, identical troops, identical conflict. One pivotal distinction. When John Moses Browning entered the U.S. Ordnance Department in 1900 carrying his prototype, the assembled experts immediately recognized his fundamental error. He'd constructed a machine gun allowing the barrel to slide backward with each discharge, harnessing the recoil itself as the energy source. Mechanically flawed, the procurement document stated, introduces alignment complications, hastens deterioration, compromises accuracy. Gas operation represents the established standard. They rejected it. For 4 decades they rejected it, until Alaska's frozen wilderness, the Pacific's stifling moisture, and the 25,000-foot altitudes of European bomber formations demonstrated something the authorities never anticipated. The most straightforward mechanism proved the most lethal. The prevailing doctrine in 1900 possessed elegant certainty. Machine guns should capture expanding gases from discharged cartridges to drive their cycling systems. Hiram Maxim had validated this in 1884 with his recoil-operated design adopted by the British military. By the century's turn, every significant military force concurred. Divert some of that explosive force, channel it through a gas tube to a piston, employ that energy to expel the spent casing and load a fresh round. The system demonstrated mechanical refinement, theoretical integrity, and battlefield success in the Boer War. When John Moses Browning walked into the U.S. Ordnance Department's procurement office with a prototype defying every tenet of this consensus, the specialists present had legitimate grounds for doubt. Browning's proposal was disarmingly straightforward. Let the barrel itself travel rearward with the recoil. Exploit that backward motion to release the bolt, eject the spent cartridge, and reset the firing mechanism. Then allow a robust spring to thrust the barrel forward again, extracting a fresh round from the belt and driving it into position. Lock, fire, repeat. The complete cycle consumed 1/10 of a second. No gas tube, no piston, no adjustment mechanisms, simply barrel, bolt, and spring. 3 primary moving components performing what the weapon naturally sought to do upon firing. The procurement officer's assessment was preserved in official documentation with bureaucratic exactness. Mechanically unsound, introducing barrel movement generates alignment complications between barrel and receiver, accelerates deterioration on locking mechanisms, diminishes accuracy capability. Gas operation constitutes the recognized standard for automatic weapons advancement. The technical reservations held merit. A moving barrel meant increased mass in motion, demanding heavier components to withstand the punishment. It necessitated looser tolerances to permit movement, theoretically sacrificing precision. And it challenged decades of European precedent establishing gas extraction as the modern, sophisticated methodology for automatic fire. By 1917, when American forces prepared for deployment to France, the U.S. military brought 2 machine gun variants into battle. French Hotchkiss M1914s, gas-operated, weighing 52 pounds, could deliver 450 rounds per minute from their strip-fed magazines. Browning M1917s, water-cooled and recoil-operated, weighed 103 pounds with water jacket and tripod mount, yet matched the identical fire rate. Army procurement documentation cited the weight differential as confirmation of gas operation superiority. Recoil operation demands excessive mass to absorb mechanical strain, the assessment declared. This constitutes inefficient design philosophy unsuitable for modern warfare's mobility demands. What those procurement analyses never acknowledged was what Browning had observed during 2 decades crafting firearms in his Utah workshop. Gas-operated weapons demanded additional components that recoil operation eliminated completely. A gas tube channeling pressure from the barrel, a piston converting that pressure into mechanical movement, adjustment screws regulating gas flow for varying ammunition types or environmental factors, seals preventing gas escape. Each component signified a potential breakdown point, a location where fouling could gather, corrosion could develop, or impact damage could disable the weapon. Browning's recoil system utilized the weapon's own mass and momentum as the operating mechanism. It was mechanical judo, redirecting force rather than creating it. The firearms community's response to Browning's passing in 1926 proved respectful yet telling. Obituaries celebrated his lever-action rifles and pump shotguns, but characterized his fixation with recoil-operated automatic weapons as an intriguing aside rather than his defining accomplishment. The British maintained confidence in their Vickers guns, refined from Maxim's original gas-operated blueprint, the JA. Armans were developing the MG-34, which employed recoil operation but with such mechanical intricacy that it demanded 150 components to function. The Americans hedged their institutional positions, sustaining production agreements for both gas and recoil designs without fully committing to either philosophy. By 1941, U.S. manufacturing facilities were producing 4 separate automatic weapon categories in enormous quantities. The M1919 Browning and .30 caliber cost $667 per unit and contained 42 components. The water-cooled M1917 Browning cost $2,165 and utilized 45 parts. The M2 Browning and .50 caliber, Browning's recoil design enlarged for aircraft and vehicle applications, cost $2,100 per weapon with 44 components. The competing Browning automatic rifle, or BR, which employed gas operation for weight reduction, cost merely $308 but required 87 parts to operate. Nobody had yet determined which design philosophy would prevail where it genuinely mattered, in the chaos and carnage of sustained warfare. The procurement discussions continued in Washington headquarters and ordnance testing facilities, technical arguments exchanging theoretical benefits like artillery volleys. Gas operation provided weight advantages and diminished felt recoil. Recoil operation delivered mechanical straightforwardness and fewer precision components. Gas systems could be calibrated for different ammunition. Recoil systems needed no adjustment. Each faction could reference European precedents, metallurgical research, and ballistic computations supporting their stance. What neither faction possessed was thorough field intelligence from actual combat scenarios testing dependability at scale. December 7, 1941, permanently altered the debate's character. When Japanese aircraft attacked Pearl Harbor, every discussion of theoretical engineering sophistication became meaningless. Within 72 hours, American forces from the Aleutian Islands to the Philippines found themselves in combat carrying whatever automatic weapons the supply apparatus had distributed. Some carried gas-operated BRs. Some carried recoil-operated Brownings. None concerned themselves with procurement philosophy or engineering consensus. They focused on one question with brutal directness. Which weapon would continue firing when everything else, training, strategy, logistics, leadership, collapsed? The largest unintended comparative analysis of automatic weapons design in military annals had commenced. Across 6 million square miles of combat landscape, from Arctic tundra to Pacific rainforest to North African wastes to European countryside, American soldiers would become inadvertent experimental subjects. The hypothesis was straightforward. Which design principle, gas operations refined energy extraction, or recoil operations crude momentum redirection, generated more dependable sustained fire under hostile conditions? The conclusion would be documented in malfunction rates, maintenance records, and after-action reports filed by individuals whose survival depended on accuracy. Attu Island in May 1943 was where physics began overriding theory. The westernmost American territory sat shrouded in fog so dense that visibility plummeted to 100 feet, with temperatures hovering at 28 degrees and wind gusts reaching 45 mph. Japanese forces dominated the elevated terrain across tundra that pulled at boots and transformed every uphill advance into exhausting toil. American soldier, as many conscripted from warm southern regions, carried 3 automatic weapon types into that frozen engagement: M1 Garand rifles at 9.5 pounds, Browning automatic rifles at 19.4 pounds, and M1919 Brownings at 31 pounds. Within 72 hours, the island would render its judgment on which design philosophy survived extreme cold. The battle's third day opened with overnight temperatures that had plunged to 19 degrees. Morning fog clung to the hillsides as assault teams prepared to strike Japanese emplacements. 214 bars had been distributed to these units specifically for their combination of automatic firepower and relative portability compared to the heavier tripod-mounted Brownings. By 11:00 a.m., 89 of those BRs had ceased operating entirely. The difficulty wasn't ice accumulating on external surfaces. Soldiers understood how to maintain mechanisms clear of visible frost. The breakdown occurred within the gas system itself, where condensed moisture from the gunner's respiration and the weapon's own thermal cycles froze solid in the narrow gas tube powering the entire operating mechanism. The physics were mercilessly straightforward. Gas-operated weapons employed a small aperture drilled into the barrel to siphon high-pressure gases from discharge cartridges. These gases traveled through a tube roughly 0.177 inches in internal diameter to propel a piston that cycled the action. That constricted tube, combined with the relatively moderate pressure that made gas operation elegant in temperate environments, created ideal conditions for ice development in sub-freezing temperatures. Any moisture entering the system, and moisture invariably entered through condensation, could freeze across that narrow opening. Even partial obstruction reduced gas flow sufficiently to cause short stroking, where the bolt failed to travel far enough rearward to expel the spent casing and chamber a fresh round. The weapon became a single-shot rifle requiring manual cycling, assuming the frozen gas system hadn't seized the piston entirely. Clearing a frozen bar demanded 15 minutes with a field stove to defrost the gas tube, then careful reconstruction while wearing gloves thick enough to prevent frostbite, yet thin enough to manipulate small components. In combat, 15 minutes was eternity. Squad commanders watched helplessly as automatic fire support evaporated precisely when Japanese counterattacks materialized through the fog. Soldiers with frozen bars reverted to their M1 Garands or fixed bayonets and continued uphill with whatever functioned. The M1919 Brownings kept firing. Maintenance records from the Attu campaign documented 41 malfunctions across 2,847 recoil-operated weapons, a failure rate so minimal that armory officers initially suspected underreporting. The technical clarification revealed why Browning's primitive design succeeded where sophisticated gas operation failed. Recoil-operated mechanisms generated violent full-stroke movement with every discharge. The bar's L hammered backward against heavy spring tension. The bolt flew open with sufficient force to propel spent casings 15 feet, and the spring crashed everything forward again to extract a fresh round from the belt and slam it into position. That mechanical violence was fundamentally incompatible with ice formation. Any moisture entering a Browning's mechanism was expelled by the subsequent shot's recoil energy. The system's substantial mass and powerful springs generated kinetic forces measured in hundreds of foot-pounds, enough to shatter any ice crystals attempting to form on moving surfaces. Where gas operation relied on capturing and directing a portion of available energy through narrow channels, recoil operation employed the weapon's entire mass as a battering ram that destroyed fouling through sheer mechanical force. It was the distinction between attempting to thread a needle with frozen fingers versus hammering a nail through ice. Sergeant Thomas Doyle of the 7th Infantry Division had grown up on a Wisconsin farm where his father taught him that any tool that froze could prove fatal in winter. He'd maintained meticulous maintenance logs since training because he comprehended that metal in extreme cold followed different rules than metal in warm weather. His M19919, which he'd named Bertha with matter-of-fact affection, developed characteristics he documented carefully. She performed better with slightly looser headspace in temperatures below freezing. The cold contracted metal sufficiently that tolerances required adjustment. She needed extra oil on the buffer spring because standard lubrication thickened into useless paste. And most critically, she operated better nearly dry than BRs ran with proper lubrication because the violent recoil action didn't require slippery surfaces the way gas pistons did. By the time American forces secured Attu in late May, the casualty reports included statistics that had nothing to do with enemy fire. 89 soldiers had fought uphill engagements with semi-automatic weapons after their BARs froze, facing Japanese machine guns that continued firing because the defenders weren't attacking through open ground. The after-action reports noted this clinical detail. BAR reliability in Arctic conditions insufficient for sustained automatic fire support. Request immediate reissue of M1919 to all assault elements. Within 2 weeks, recoil-operated Brownings were distributed to every frontline squad in Alaska Command, while gas-operated BRs were reassigned to reserve units in temperate zones. Doyle wrote home in June with the plain language of someone who'd watched theory collide with reality. The Browning is ugly, heavy as sin, loud enough to deafen you, and when your bar is frozen solid and the Japanese are coming uphill in the fog, that ugly .30 caliber is the most beautiful thing you've ever seen. His maintenance logs, filled with precise notations about temperature, malfunction causes, and comparative reliability, reached Washington by July. The Ordnance Department's response was documented with bureaucratic caution. Isolated incident. Arctic conditions not representative of standard operational environments. But the Brownings trial was far from finished. The recoil-operated design that had survived the frozen north was already deployed across every climate zone where American forces battled, and the next testing environment would prove even more hostile than Attu's ice. The Pacific Theater's humidity, heat, and corrosive salt air were waiting to deliver their own verdict on whether simplicity or sophistication survived where it genuinely mattered most. The Pacific Theater demonstrated that humidity could prove as lethal to automatic weapons as Arctic cold. Island warfare from Guadalcanal to the Philippines subjected firearms to conditions that transformed engineering sophistication into fatal weakness. Temperatures range from 90 to 105 degrees with humidity levels between 85 and 95%. Salt-laden air carried microscopic corrosive particles that infiltrated every gap and crevice in mechanical assemblies. Marine Corps armorers discovered that even properly maintained and lubricated BARs would develop internal pitting within 48 hours of island air exposure. Gas-operated weapons, with their constricted tubes and precision-fitted pistons, became incubators for rust. New Georgia Island in July 1943 became the location of an unintended comparative analysis that would reshape American automatic weapons doctrine. The 43rd Infantry Division landed with 412 M19 Brownings, 289 BRs, and 156 M1 Garands. All three weapons fired identical .30 caliber ammunition, confronted identical environmental conditions, and received comparable maintenance from soldiers with equivalent training. After 12 days of continuous combat in 94-degree heat and near-constant rainfall, the operational statistics told a story that procurement officers in Washington could no longer dismiss as isolated occurrences. M1919s remained operational, a 96.4% functionality rate. Only 15 weapons had been deadlined for parts replacement, primarily worn buffer springs and cracked feed pawls from sustained high-volume fire. 177 bars were still functional, a 61.2% rate. 112 weapons sat deadlined, with 78 failures attributed directly to gas system corrosion that blocked or restricted the narrow tube connecting barrel to piston. 40 M1 Garands remained operational, an 89.7% rate, with 30 rifles deadlined for gas system pitting that caused short-stroking. The technical explanation revealed why Browning's supposedly archaic design dominated in tropical conditions. Gas tubes in BARs and M1s measured roughly 1/16 of an inch in internal diameter, narrow enough that a single pinhole of rust could obstruct 40% of gas flow. The high-pressure gases traveling through those tubes carried moisture and carbon residue that deposited on internal surfaces. In humid tropical air, that residue absorbed atmospheric moisture and formed corrosive compounds overnight. Even meticulous cleaning couldn't prevent microscopic pitting that gradually restricted gas flow until the weapon failed to cycle properly. The M1919's recoil mechanism utilized components that were larger, more robust, and deliberately over-engineered for punishment. The bolt weighed 1.8 pounds and was driven by a spring rated to 90 pounds of compression force. Those massive components didn't care about surface rust or minor pitting. The bolt's momentum and the spring's violence overcame friction that would halt a gas piston completely. Where gas operation relied on channeling pressure through narrow passages that demanded cleanliness, recoil operation simply hammered through contamination with raw mechanical force. Corporal James McWillis of the 164th Infantry had been a bank clerk in North Dakota before the war, and he brought an accountant's meticulous precision to jungle combat. His waterproof notebook contained entries that would later become primary source documents for post-war reliability studies. Each weapon malfunction, eaning interval, and parts failure was recorded with the same methodical detail he'd once applied to loan applications. The August 15, 1943 entry was characteristic of his approach. Bar number 7738, removed gas plug, discovered green corrosion blocking 70% of tube diameter, reamed clear with cleaning rod. Weapon functioned for 47 rounds before seizing again on short stroke. Swapped for M1919 number 42891. Fired 2,400 rounds across 4 days. 0 malfunctions. Gun exterior shows heavy wear and surface rust, but continues cycling normally. McWillis had learned on Guadalcanal that reliable weapons were the difference between survival and death. His entire squad had been killed in the first week, except for himself and the M1919 gunner. an event that convinced him that documenting weapon performance was more important than any other record-keeping he'd ever done. His 18-month maintenance log covered 47 different weapons across New Georgia and Philippines campaigns, tracking patterns that individual soldiers couldn't see. M1919 malfunctions clustered around ammunition problems, defective production lots with inconsistent powder charges, corroded belts that caused feed issues, or damaged cartridges that failed to extract. Bar malfunctions clustered around the weapon itself, gas system fouling, recoil spring fatigue, and extractor breakage from the additional stress of fighting through reduced gas pressure. The pattern pointed to a fundamental design truth that procurement theory had missed. Gas-operated weapons added complexity in exchange for theoretical advantages that disappeared under field conditions. The weight savings of gas operation, a 19-pound bar versus a 31-pound M1919, meant nothing when the lighter weapon spent 60% of combat time deadlined for maintenance. The reduced felt recoil of gas operation was irrelevant when the weapon wouldn't cycle. And the elegant engineering of capturing barrel gases became a fatal flaw when tropical humidity turned those narrow gas passages into rust-producing chambers. In October 1943, Marine Corps Gazette published an article titled Automatic Weapons Reliability Under Tropical Conditions that represented the first official acknowledgement of recoil operation superiority where combat conditions tested design philosophy at scale. The article's conclusion was carefully worded but unmistakable. Comparative field data indicates that recoil-operated crew-served weapons demonstrate significantly higher operational readiness rates than gas-operated designs in high-humidity environments. Recommendation: prioritize recoil-operated machine guns for Pacific theater deployment. Army Ordnance responded with bureaucratic subtlety, quietly revising procurement priorities without admitting that 60 years of gas operation consensus had been mistaken. Gas-operated designs would continue for rifles, where individual soldiers needed portable weapons and could perform detailed maintenance between engagements. But for machine guns, crew-served weapons where reliability was literally life and death, where sustained fire support determined whether assault succeeded or failed, Browning's dismissed recoil system became the institutional standard. The shift happened in production schedules and supply requisitions rather than official announcements. But every combat unit in the Pacific watched their weapons mix shift toward the guns that kept firing when everything else stopped. The M2 Browning proved Browning's recoil design at its most extreme scale. Chambered in .50 caliber and weighing 84 pounds without mount or ammunition, the M2 was recoil operation scaled up for aircraft and vehicle use. It fired rounds half an inch in diameter at rates between 450 and 550 per minute, with effective range exceeding 2,000 yards. By mid-1944, the 8th Air Force was flying 1,000 bomber raids over Germany. Each B-17 Flying Fortress carried 13 M2 Brownings distributed across waist positions, tail turrets, ball turrets, and nose guns. That meant roughly 7,800 rounds of .50 caliber ammunition per aircraft and 13 independent firing positions that needed to function flawlessly at 25,000 feet, where temperatures dropped to 40 below zero and oxygen levels required crews to wear masks. Luftwaffe pilots began reporting something unexpected in their combat debriefs. American gunners sustained fire longer than German gunners in comparable defensive situations. The observation puzzled German intelligence because training quality was roughly equivalent and ammunition supplies were similar. The answer wasn't training or logistics, it was mechanical. German bombers used MG-131 machine guns in 13mm caliber, which were recoil-operated like Browning's design, and MG-151 cannon in 20mm, which used gas operation for higher power output. The MG-151s delivered devastating hitting power when they worked, but Luftwaffe armory records documented malfunction rates between 8% and 12% during sustained fire sequences due to gas system overheating at high altitude. American B-17 gunners filed 23,000 combat reports between January and June 1944. M2 Browning malfunction rate during those engagements measured 2.1%. The technical explanation revealed why Browning's recoil system dominated at altitude, where temperatures, pressure, and sustained fire created conditions that defeated sophisticated engineering. The M2 used the weapon's own violence to stay clean. Every shot generated such powerful barrel movement, 0.75 inches of rearward recoil travel, that carbon fouling was literally shaken loose before it could accumulate. The mechanism could fire 200-round bursts without cleaning, a capability that gas-operated designs couldn't match because their narrow gas passages would choke on carbon deposits long before reaching that volume. Technical Sergeant Robert Harper, of the 91st Bomb Group, had been a Lutheran minister's son from Iowa before the war, and he approached B-17 gunnery with monk-like discipline. Between missions, he spent hours disassembling, cleaning, and understanding every component of his waste gun's M2, believing that mechanical excellence was a form of moral duty to his crew. Other gunners noticed his methods, and his waste position became an informal training station where nervous replacements learned that steady maintenance created steady fire. Harper's special talent was mechanical diagnosis under combat conditions. He could identify malfunction types by sound and feel even in darkness at altitude while wearing oxygen masks and sheepskin gloves thick enough to prevent frostbite but barely thin enough to manipulate charging handles and feed mechanisms. His 94 mission record with 0 M2 failures became legend in the 91st. 3 separate fighter attacks had been survived because Harper cleared malfunctions that weren't actually his gun's fault: damaged ammunition, twisted feed chutes, or debris in the belt, while other positions went silent. He'd watched B-17s drop out of formation with guns that stopped firing at the worst possible moments, and he'd concluded that the difference between survival and death often came down to whether a gunner understood his weapon well enough to diagnose problems in seconds while fighters closed a firing range. The M2's mechanical simplicity made that understanding possible. 44 parts total: barrel, bolt, spring, and feed mechanism. A gunner could learn every component's function and failure mode in ways that complex gas-operated systems made impossible. Harper wrestled with theological questions that disturbed his sleep between missions. Whether praying for weapons to keep killing was compatible with Christian teaching occupied his thoughts during the long bomber streams to target. He eventually concluded that protecting his crew was the prayer that mattered, that keeping his M2 functioning was how he served both God and the 9 other men whose lives depended on defensive fire. That resolution let him serve with clear conscience through missions where sustained bursts heated his gun barrel to glowing red and smoke rose from his gloves when he touched metal surfaces. The M2 kept cycling through that abuse because its recoil system didn't care about heat the way gas-operated mechanisms did. By early 1945, the air war over Europe was effectively won. B-17s flew in formations so massive that Luftwaffe fighters rarely pressed attacks home. But ground combat revealed a new challenge that critics seized upon as evidence that Browning's design was obsolete. German MG-42s were outpacing M19-19s in pure cyclic rate. The MG-42 fired 200 rounds per minute using gas operation and complex engineering that required over 150 parts. The M1919 fired 400 to 500 rounds per minute with its simple recoil mechanism and 42 parts. Procurement memos argued that the war had proven rate of fire mattered more than reliability. Modern combat demands suppressive volume, the analysis stated. Mechanical simplicity cannot compensate for insufficient cyclic rate. The criticism gained traction in Washington offices where procurement officials had never heard an MG-42's distinctive ripping sound or watched German gunners struggle to keep the weapon fed and functional under sustained use. The high cyclic rate that impressed observers on firing ranges became a liability in combat, where ammunition supply, barrel changes, and mechanical stress determined whether weapons remained operational through extended engagements. But those realities were difficult to quantify in peacetime analysis, and the institutional momentum toward complex, high-rate-of-fire gas operation was building again, just as it had before Attu, before New Georgia, before the numbered missions over Germany had proven otherwise. The final accounting would need to wait until someone compiled combat data at a scale large enough to settle the question permanently. In June 1945, U.S. Army Ordnance conducted the largest automatic weapons study in military history. 94,000 after-action reports from the European Theater, Pacific Theater, and Mediterranean Theater were compiled, covering every major engagement from Normandy to Okinawa. The analysis was designed to answer 3 questions that had generated 40 years of institutional debate. Which design principle produced lower malfunction rates under field conditions? Which system required less maintenance during sustained combat operations? And which weapons remained operational longer under continuous use? The data would either vindicate 6 decades of gas operation consensus or prove that Browning's dismissed recoil system had been correct all along. The malfunction rate analysis. Measured failures per 10,000 rounds fired across all combat conditions and theaters. M1919 Brownings recorded 8.7 malfunctions per 10,000 rounds. M2 Brownings recorded 9.4 malfunctions per 10,000 rounds. Browning automatic rifles recorded 31.2 malfunctions per 10,000 rounds. Captured German MG-42s, analyzed from battlefield recovery and interrogation of Wehrmacht armorers, showed 18.9 malfunctions per 10,000 rounds. The pattern was unmistakable. Recoil-operated crew-served weapons outperformed gas-operated designs by factors ranging from 2.1 to more than 3.1, depending on the specific comparison. Maintenance interval data revealed an even starker difference. M1919s averaged 2,400 rounds between required cleaning that interrupted combat operations. BRs required cleaning every 800 rounds to maintain reliability. MG-42s needed cleaning every 1,500 rounds according to Wehrmacht maintenance protocols. The explanation was mechanical rather than metallurgical. Gas-operated weapons accumulated carbon fouling in their narrow gas tubes and piston assemblies at rates that eventually choked off the pressure needed for reliable cycling. Recoil-operated weapons expelled fouling through the violence of their own operation, with each shot's barrel movement and bolt impact shaking loose deposits before they could build to critical levels. Operational life expectancy measured how many rounds a weapon could fire before requiring major parts replacement rather than routine maintenance. M1919s averaged 95,000 rounds before needing barrel replacement, bolt replacement, or spring replacement. M2s averaged 127,000 rounds before major parts failure. BARs averaged 42,000 rounds before gas system components or operating rods required replacement. The data pointed to a fundamental truth about mechanical design under stress. Fewer parts meant fewer failure points, and simpler mechanisms tolerated wear that would disable complex systems. The report's conclusion was written in careful bureaucratic language that nonetheless represented a complete reversal of 60 years of institutional consensus. Recoil-operated designs demonstrate superior reliability across all environmental conditions due to reduced component count and increased mechanical tolerance for fouling, corrosion, and wear. Gas-operated systems offer theoretical advantages in weight reduction and felt recoil, but demonstrate higher failure rates under sustained combat use. Recommendation: recoil operation should be considered the primary design principle for future crew-served automatic weapons development. Technical Sergeant Raymond Jacobs, of the 1st Infantry Division, had landed at Omaha Beach in the 3rd Wave on June 6, 1944. He'd watched half his company cut down in 20 minutes of German machine gun fire that swept the beach in methodical traversing patterns. He'd concluded that morning that the only honest way to honor the dead was to remember exactly what happened without embellishment or mythology. And he'd kept a detailed journal documenting not heroics but mundane details, serial numbers, maintenance schedules, ammunition expenditure, and the daily survival of objects under extraordinary stress. His M1919 carried serial number 44827. That weapon went from Normandy hedgerows to Aachene's urban ruins to the Rhine crossing, 11 months of continuous combat. The barrel was replaced twice after extended fire missions that left the rifling worn smooth. The buffer spring was replaced once after it began showing compression fatigue that affected cycling speed. The extractor was replaced 3 times after breakage from sustained use. But the bolt, barrel extension, and receiver, the core components of Browning's recoil system, never required replacement. Jacobs brought the weapon home to Chicago and preserved it in his garage as a physical memorial to the 11 months that had kept him and his squad alive. Between 1941 and 1945, U.S. factories manufactured 2.08 million M1919 Brownings and 400,000 M2 Brownings, 2.48 million recoil-operated machine guns total. Those weapons fired an estimated 12.8 billion rounds in combat across every theater where American forces fought. The documented malfunction rate across all platforms, conditions, and operators measured 3.2%. No competing design, American, British, German, or Soviet, matched that reliability figure. The numbers represented more than engineering triumph. They represented the survival of soldiers who'd been issued weapons that worked when nothing else did. The M2 Browning that John Moses Browning had designed in 1921, the weapon that procurement officers had called obsolete in favor of gas operation, remained in U.S. military service for the next 100 years. Some M2s manufactured in 1933 were still operational in Pacific Shore batteries at war's end. weapons that had fired over 200,000 rounds each without catastrophic failure. Gas operation produced 19 major military designs adopted by various nations between 1900 and 1945. Browning's recoil operation produced 6 major military designs in the same period. By the year 2000, every gas-operated design from that era had been retired and replaced. The M2 remained in service. Browning had died in 1926, believing that institutional inertia would never fully embrace his recoil-operated designs. He'd spent decades watching procurement boards defer to European precedent and favor sophisticated gas systems over his mechanical simplicity. What he hadn't lived to see was combat data from 3 continents proving that his dismissed idea, using recoil instead of fighting it, created the most reliable automatic weapons in military history. The genius wasn't complexity, it was clarity. He'd seen that every weapon generates violent recoil energy, a force that engineers tried to dampen or redirect. He'd simply asked what would happen if that force powered the weapon itself. That question, called mechanically unsound, in 1900 became the foundation of American automatic weapons doctrine for a century. The simplest mechanism, powered by nothing more than Newton's third law, outlasted every competitor because it did one thing perfectly. It kept firing when everything else stopped.